Hello, welcome. Thank you for coming. We are here today to talk about one of my favorite subjects, service meshes. And in particular, I'm really excited today because with me is Prateek Sahu. Prateek?
Hey guys, I am Prateek. I am a grad student at UT Austin, and I was actually looking at not looking at service meshes. I was looking at function as a service and serverless applications about a year and a half back when I met Lee, and then we started looking down this path of service meshes and performance impacts, and here we are.
Yeah, Prateek, clearly you were focused on the, well, I don't know, or not on the right thing. We have to, service meshes is where it's at. So that was what about a year ago now. So I'm just ecstatic that we're going to share some of what we've been studying. Some we've I've sort of talked in this space for a while. I've written actually a couple of books on service meshes, and believe it or not, am authoring two concurrently at the moment. And well, we'll see if I'm, I guess, still married by the time that they publish. But service meshes have been a real focus of mine. There's some questions that as I've been focusing there, and as you and I have been working together now, that we've been trying to answer. I'm excited that we get to answer some of those today, some that we haven't gotten to speak to before. So just, I guess, by the way, the one takeaway from this slide here is the URL there is where you can find a copy of this deck and other talks that I give. But again, happy to be joined by Prateek, if I can get the slide to advance. Or advance 5 slides all at once. So sorry about that, Prateek.
No worries. I am kind of looking into the research aspects of service meshes and looking into interesting findings to share with you folks. I have been working on service meshes for a while, and there are a lot of interesting research topics in this area, but we'll only focus on a couple of them in this particular talk. And yeah, feel free to reach out to us and join the community to know more and contribute and discuss interesting stuff.
Nice. Speaking of that, those interesting things, this is, well, a top level list of why it is that people consider service meshes interesting. And this is really more in hard terms of why it is that they consider service meshes interesting. Different people break this down in different ways, but there's buckets of functionality that service meshes bring to bear. They improve the resiliency of your services, whether they're micro or not. They provide a lot of fine-grained traffic control, traffic management over all the requests that are flowing into and through your services or out of your services. They give a lot of built-in observability. We like to talk about that in terms of the observability being uniform. So the telemetry that a service mesh will generate based on the requests that it sees, really helpful, really enlightening, takes the blinders off for a lot of people. And there's a whole category around security, of what requests can be made, of what services and when and how often and how much. And there's a lot that can be done inside of a mesh. And I'm convinced, or I know for sure, most of us out there have yet to go horribly deep. A lot of folks have yet to go beyond, even to have accounted for all of the 4 things that I'm talking about here. Many people have yet to go further than that. A lot of people are attracted because of those, those various features. Other people are attracted to a mesh because sort of similar to what they've experienced with Docker in modernizing their applications, in modernizing their infrastructure. They are able to modernize existing apps by bringing them onto the mesh. Again, we often speak about service meshes in context of microservices, and it's true that sort of the more services you have, the more that you will benefit, that you will find that you'll benefit from a service mesh. That doesn't mean that service meshes don't provide for existing applications that are not containerized. They do. Now, having said that, not all meshes provide for non-containerized services, but many of them do. The nice thing is you can kind of, sort of with an asterisk, you can kind of get there for free. I'm just noticing a behavior of the system, by the way. When I try to advance a slide, it takes about 10 seconds to advance. So I'm going to try to click 10 seconds ahead, and we'll see if it works. Other reasons why people come to a mesh is to avoid baking in infrastructure concerns into their code. They don't want to, expend a bunch of energy on duplicative infrastructure concerns that the infrastructure can actually take care of, that in the presence of a service mesh, a lot of those features that we just talked about are there. They can avoid having to bake that, right? Use a client library, which we're going to take a look at one here later, to address those concerns. Rather, they can get retries and enforce deadlines, cancellations, and circuit breaking, and many other things that they might have otherwise had to put into code. Your infrastructure can handle that for you. So one of the interesting things I think that is arguably the most powerful phenomenon about a service mesh is the notion that often the responsibility of whether it's the developer or the operator or someone else who's responsible for identifying what rate limits should be set for a service, how often a service should retry, or any number of these configurations, like whether or not a service should be assigned an individual certificate, have its own identity, have that identity rolled, have that identity managed, that all of those things, I think who's responsible for that in a given environment is often diffused and confused between which of these two teams that is. The hope here is that when you've got a piece of infrastructure like a service mesh, you're able to identify all of how you'd like for that litany of concerns that I just prattled off, how you'd like for those to be configured and behave. When you've got that in a set of configuration, when you've got that in YAML, it is no longer a finger pointing game. Rather, it's a singularly addressable concern, and it becomes self-evident who's taking care of those things. So I think that's really powerful. The way that those two teams are able to begin to iterate independently of one another, they're able to move more quickly, and they're able to, both of them, rapidly identify what a given retry count is for a service, for example, because it's there in the configuration. It's not buried in code, or it's not even in the code. It's not even present. So really interesting thing about a service mesh. As we get into more of what we're going to speak about the analysis of network functions and how service meshes provide various network filters, various traffic filters, it's important to consider, and it's important to understand that there are a variety of different service mesh architectures. And that's in part because there's a variety of different service meshes out there. Yes, it's a bit meshy out there. There's a landscape here that tracks service meshes, about 20 or more. And actually, as it turns out, there will be an announcement from a vendor that you all are familiar with before the year is out. A really exciting announcement, I think, but it'll make for the 21st service mesh. So more of them keep coming. Clearly, people are seeing value in the meshes. because there are as many as there are, and which is a great thing, by the way. I mean, it's I think the analogy here is that a service mesh is a tool like other tools. If you there's a reason that people purchase toolboxes, because you generally can't just use one tool for all of the jobs that you have, and it's kind of the same thing for a service mesh. They're built to have some similar capabilities, but they're also built for different sized environments, different use cases, built in different ways, and using different languages, different architectures. And so I'm quite pleased that there's choice out there. It's not a one size fits all necessarily, but because of that, there are service mesh abstractions, specifications that are coming forth. I participate as a maintainer in the service mesh interface, which is essentially a standard. Well, it's almost like if I can, we'll see if people get upset with me for this, but if it's almost like Terraform is as a utility to multiple clouds. Service mesh interface provides a standard interface behind which you can plug in a given service mesh. Probably better analogies here are something like CNI, the container network interface. It gives you one API, one surface for you as an adopter or you as an integrator to get at service mesh functionality, irrespective of what service mesh you're using. So that's great. There's another one here called Hamlet. It is focused on federation of service mesh catalogs, if you will. So one given service mesh will have any number of services, any number of workloads that it's supporting. And when you've got a second service mesh, whether it's of the same type or not, you often want those things to be able to speak to one another. And that's kind of the focus of Hamlet. There's a third specification, a third abstraction that we're going to talk about today. And it's the Service Mesh Performance Specification, or SMPS. It's really a format that standardizes the way in which you capture and characterize the performance of a service mesh. So SMPS is a vendor-neutral standard. It's one that Layer 5, which is the community that Prateek was talking about, the service mesh community, has been working on for a while. Really had gotten started in conversation with the Istio performance and scalability team. So with the Googlers there. And since we'd been speaking about it and talking about it and advancing it and working through it, we've begun to discuss it inside of the CNCF, inside of SIG network in the CNCF. So there's a service mesh working group that all are welcome to come and participate in. But where we also advance this specification. The spec, like I said, it directly provides a description, how to describe and capture, how to characterize the performance of not just your service mesh, but also the fact that that's highly dependent upon what type of workloads your mesh is supporting, how your mesh is configured, how much you're asking it to do. How big or small of an environment, how many nodes and what size nodes you're running. So many, many different variables. And so it helps standardize how you capture that. From there, it then facilitates some interesting things. And one of those is an apples to apples comparison, either between service mesh deployments of the same type or different types, but maybe more importantly, it facilitates you gauging that for yourself and having a standard way to capture the performance of your mesh, the configuration of your mesh. There is an implementation of this specification today, the canonical implementation, in a tool called Meshery. Meshery is the service mesh management plane. It's a multi-mesh management plane. It is compatible with SMI. It was that compatibility was announced, sort of launched or announced at the launch of SMI. It's now compatible with the service mesh performance spec. There are, well, gosh, I think 3 interns being sort of working around SMI and working around Envoy and around Meshery through the Google Summer of Code, through the CNCF, and through Community Bridge. hopefully through Google's Season of Docs here shortly as well. And so there's a few different goals of this tool, and it's important that we talk about this tool because it's what's been facilitating our performance analysis, the analysis that we're going to speak about here in a moment. Originally, there was a lot of ask in the community when people are first learning a mesh. They often ask themselves, well, hey, what's the overhead of one versus the next? Which one should I use? And we've publicly spoken on this, a number of times. Please disregard these, like, I don't know, year and something ago old stats. Rather, it was really just trying to show that, like, hey, when console first came out, really it was only facilitating MTLS. So it really wasn't doing much in comparison to maybe Istio that you were asking it to do a lot more. And so anyway, one of the things that it was intended to do is that it still does that. It also does a bit of best practices analysis. So if you're running a mesh and you're using Meshry to do some performance management, you can also do some configuration management. It will analyze the configuration of your mesh and tell you if you're doing it wrong, or maybe it'll tell you you're doing it right. It's, I think, interesting to look at where a tool like this fits in. When you look at service meshes, you talk about the data plane and the control plane. And this is a generic view of what a data plane and control plane often look like. You can also layer on a management plane. For those of you who are network engineers or have done network administration, I think that's a familiar term. And in this, management planes are capable of any number of different things. The functionality that we're talking about here is really around load generation and statistical analysis of the performance of a mesh. What we're showing here is that Meshry gives you sort of choice of load balancer. I'm sorry, not load balancer, load generator between Fortio, WRK2, Nighthawk, and it will generate load and do an analysis. Today, it'll do that against any one of these 6 service meshes. And it does that through adapters, through service mesh adapters. More adapters are being added in the community. So good. Now that you're familiar with part of the tooling that we use and that we're going to show you today, let's talk about our workload. So in the course of, this has been a discussion of Prateek and mine and some others for quite some time on, well, trying to make sure that we're using representative workloads as we're studying and analyzing traffic, service mesh performance and kind of traffic statistics. That, like we were saying, that's highly dependent upon the environment that you're performing your study in. Part of that environment is your workload, your app. And so it was just a few months ago that we'd worked to create a sample app called Image Hub. It's actually, if you're familiar with Docker Hub, it's really similar. It's from something of a ripoff of the Docker Hub. It doesn't actually work. It's just a sample app. But the interesting thing, and the reason that we had created this sample app as opposed to using the other sample apps that Meshry supports, is because we wanted to highlight the fact that it's not just fine-grained traffic control that a service mesh can facilitate, but it is also the fact that a service mesh can be told to have quite a bit of intelligence in its data plane. And the example here that we won't take you through today, but we'll take you through some network performance instead. But the example here is the notion that the app has, much like any SaaS offering that you might use, you'd sign up as a user and you have different subscription plans that you sign up for. Well, this app has subscription plans, but it doesn't have any way of enforcing people to stay within the bounds of those plans. And so we use a service mesh to intelligently rate limit and kind of filter a user's usage based on their consumption. And that intelligence happens not within the app, but rather within the data plane. So hopefully this sample app enlightens, expands some of your horizons to, well, expect more from your infrastructure, to leverage your infrastructure a bit more. This is, it's a very simple app. It's 2 Docker containers. There's a Vue UI, or a UI written in Vue, running in one container. There's a backend that's your image, your Docker image storage service, and it runs a set of APIs and runs a storage service. We're able to take this sample app and deploy it on top of a mesh. And the mesh that we've chosen is Console, for a couple of different reasons. One of which is because Console uses Envoy as its data plane proxy. And Envoy is capable of incorporating WebAssembly modules, WASM modules. We'll talk about WebAssembly more in a moment. But there's a lot of power in the ability to load and dynamically reload WebAssembly filters. These filters are highly capable. They're able to see the same network traffic, the same requests that come through that are addressed to your services. They're able to interpret, grab those requests, facilitated through Envoy in this case, and apply some logic to them. And an example of that logic was what I was just speaking about a moment ago, which is to say that this Image Hub sample app uses a WebAssembly filter that runs inside of Envoy. And this particular filter is written in Rust just for performance reasons. I won't re-describe what the sample app does because that's kind of for a different talk. But suffice to say, I guess I should note that today Console doesn't support this configuration and the use of WASM filters out of the box. And I won't speak on behalf of the product management team there. I would just, I would say that I think, your best get, I would say to pay attention and maybe look out for that possibility. So with that stage set, we're going to talk about performance. And there's a number of interesting things that Prateek and I and the collection of those who are working in this community have uncovered. We're here to share a few of these things with you today to the extent that we can. And I think as we do, it's probably important to recognize that, when we're talking about performance and measuring performance, wow, look at the time fly. I just realized that I've been talking. So I will pick up the pace. When we're talking about performance, it's not easy to hold all these variables in place. And so that's also why when you see a bunch of benchmark statistics published, it's sometimes I'll cringe. I'll just speak for myself there because it's so easy to get a performance study wrong. To do one very well, it sometimes takes a PhD student. So thank goodness for Prateek. I said that we were going to talk about WebAssembly, a very interesting technology that's been around for a little while and is now kind of coming toward the service mesh landscape. And we're excited about it. I guess I won't describe it further given the time. Some of the insights that we've been able to garner over the last number of months here have been a couple of ways of looking at and sort of assessing the overhead of the power of a mesh. Like, hey, and you would expect probably that the more that you ask a service mesh to do, the more filtering of those requests and of those traffic, the more overhead that might be incurred. There's different ways of measuring overhead. We're going to talk a lot about latency today. Latency being one of those critical pieces of information that you wanting to provide your users a good experience with, or consumers of your services with a good experience. And what we've begun to do here is compare kind of 3 different ways of providing traffic filtering in your data plane. One is to continue to use client libraries, language-specific client libraries, or just the standard libraries of the language itself to facilitate some of these network functions. In this case, what we're talking about here is rate limiting specifically. This is just what we had studied here. And the statistics that we're seeing is in the environment that we were within, we went through a couple of configurations, set the rate limit to be,
we have run. Let me take up the results in the way that we tested this in two different environments, if I may. We implemented a rate limiting feature inside the Go application itself, and then we also implemented a rate limiting feature as in our Rust WebAssembly, and plugged it inside the Envoy sidecar proxy and removed the rate limiting feature from the Go application. What we would have expected is that if the rate limiting is inside the application itself, then it should perform better. But since it's WebAssembly and the network traffic that is coming through the sidecar proxy and being routed through the sidecar proxy to the application can be processed in the sidecar itself, and it does not need to go have the overhead of being transferred to the application again. Because of that, we see a fair amount of benefits. The experiment, the rate limiting is set at 100 requests per second. So when we send 100 requests, there are no errors. And when in the native Go client, we see a latency of about 3 milliseconds, whereas if we do not have the rate limiting feature in the Go, but we put it inside the WASM, we see a lower latency of 2.1 milliseconds. Again, to reiterate, there are no errors in here, like none of the requests are being stopped, and still we see a benefit in latency. As we go higher to a higher request, like 500 requests per second, we expect 100 of them to pass and 400 of them to fail. And you can see that there is even more significant benefits when we see the request being filtered out from the sidecar proxy itself. Meshery has this amazing feature where you can leave the RPS blank, and it will automatically try to load the service as much as possible, like try to measure how many requests it can actually send in a closed loop circuit. And with the native Go client, we saw that it can only service 4,400 requests. Well, 100 of them go through, and the rest 4,100 are error messages. But since they go to the client library and then return the error, they incur a larger overhead and hence a lower rate request per second. On the other hand, since we have a WASM filter inside the sidecar container, the requests were being filtered way more efficiently when we use this feature, and we saw almost like 1,000 more requests being handled. Although that this is a very simplistic example, but when we see that even in a simple example, we see such significant difference in latencies. So as and when the functionality gets larger and more complex, these latencies will grow only more significant. One new thing, not new, but good thing about WASM is you can only use WASM filters as and when you need. like we do with kernel modules in our old age days, we can insert kernel modules and remove them to lower our binary overhead. We can do the same with WASM. If we need a particular feature, we can load it up, and if we don't need it, we can remove it. And that speaks to the power that WASM provides us with in service mesh and these microservices infrastructures.
And so we'll try to get the slide advanced. It'll take a moment. I just realized we're go back one, and so to Prateek, please interrupt me as I go here. But outside of just looking at the overhead differences in how you take a given network function like rate limiting and how you implement that and the differences in the overhead of those implementations, you also can take different types of network functions like path-based routing, round-robin load balancing, or context-based path routing, and analyze, compare them as individual network functions and compare and contrast their speed. And in the same environment that we were using for the other tests that we just talked about, we were seeing that really just a single path-based routing being having a higher performance, while round-robin load balancing taking a slight more hit in terms of latency and in terms of throughput, actually, for the given time period. And then context-based routing, as you might expect, is a little more powerful, and it also is comparatively slower than the other two. And so we'll see if by the time we take some Q&A, we'll have some data points to share there specifically. Lastly, we will say that, and Prateek, again, feel free to interrupt on this. I'm trying to hurry, but just
yeah. So this was a great experiment that came by us while we were running other experiments. Is how do we optimize our average response times? So we tried to run one of the tests, and as you can see in this graph, we saw that the response that we got could be bucketed in separate chunks. That is, in bucket 1, we did get a few of these responses, but majority of the responses came back in bucket 3. That means our service is able to process requests as low as, I'm sorry for the small figures, it's around like 12 to 18 milliseconds. But still, majority of our requests come back around 50 to 60 milliseconds. That means that there is potential in our service to respond in 12 milliseconds. And we tried to figure out how do we optimize this. And if we take the smallest segment bucket, that is bucket 1, and we try to see what is the maximum number of requests that were handled in the histogram, that is at 14 was around 45 to 50 requests, and we divided it by the number of threads that we were running, that is 2 threads. And when we did that, lo and behold, we got most of our responses in the bucket 1 range. Lee, could you share that? Yeah, so we reran the test with a lower request per second, around 25 to 30, and we saw that most of the responses were received in bucket 1. So there is tons of potential that we should gather by looking at these performance metrics, and there is tons of optimizations that we can do in this scenario as well.
Nice. Very good. And to share just a couple of those best practices, given the time that we have left, it's to probably go take advantage. There's actually a long list of service mesh benchmark testing best practices, some published by Envoy in that project, some published by Istio in that project. And it's actually it's because of those best practices and the people, as many people that have questions about performance as they do, that Meshery as an open source tool has been created to empower people to easily reproduce these tests, to persist your results, to baseline your environments, to use different load generators because they do statistical analysis differently, to compare your configuration changes, to test your workloads on and off the mesh, to do it against different meshes, like sort of on and on. With that, we recommend you give that tool a shot, but also recommend that you jump into this community here where Prateek and I both hang out quite a bit. And speaking of hanging out, we're going to be hanging out taking Q&A right now. So please bring your questions.
Thanks.
Boo!
Hey guys,
Oh,
we're here to answer any questions. Sorry about the screen share. For some reason it was off. Hope you all followed the link shared by Lee on his page.
boy, kudos to those who've stuck it out throughout this talk. The video being out of sync has been, well, it's been impressive to see those stick around for the end. So I know we've seen a couple of good questions coming through. And so trying to answer a few of those, it'll be a little bit easier, actually, I think, to verbally speak to those. So that's nice. One of them was just about Rust as, you know, in terms of its performance and using Rust-based Rust-based filters inside of WASM VMs. To characterize part of that answer is that Envoy itself is written in C++. There are certainly performance comparisons that you can do between kind of popular languages in this space: Go, C++, Rust. You know, if there were folks from the Linkerd project here, they would espouse the performance and some other characteristics of Rust. And I think that by and large, it probably is the case that Rust would be would have some both performance characteristics and some others that if you're doing intense intense filtering of network traffic within a WASM environment, that you're seeking out Rust, or even outside of a WASM environment. So the Linkerd service proxy is written in Rust. If you don't use WASM though, and if you are using Envoy as your service proxy, Envoy is written in C++, and so writing a native Envoy filter in C++, is going to be a bit quicker. And the reason I pause for a moment is to say that Prateek has, well, in the time that we've recorded this talk, published some additional metrics or some additional analysis. Prateek, maybe I'll try to share the link. I think that this is fresh as of last minute, so.
Yeah, like we can expect Rust to be quite performant because the language was developed to be performant. But definitely, it's a great question that we can do some additional research to see which among, as a WASM filter itself, if Rust or C++, which of them is performant. But like, I would expect Rust or C++ to be one of the best in terms of performance.
Cool.
So there's a question: does the Meshery help to manage and configure WASM filters? If not, extension able to do it? It's a very interesting question. So WASM filters in service meshes is still very much an active developmental scope for a lot of service mesh. Meshery provides adapters for you to try out a lot of these service meshes, and as and when the service mesh starts supporting WASM filters, we will try to integrate the best we can, and if there are APIs, we'll try to write an adapter so that you can configure WASM filters in the service mesh in a generic fashion.
Further Prateek's answer, I'll go ahead and publish a link where those that are curious about use of Meshery and Meshery's injection or management of the loading and sort of dynamically reloading of WASM filters in Envoy-based service meshes. The link that was just shared is to a sample app called Image Hub. And so that sample app is orchestrated by Meshery. It deploys actually into a console-based service mesh. And console in its current release doesn't, I don't think it doesn't officially support the use of WASM filters, but because it is using Envoy as its sidecar technology, it inherently does. And so, near as I understand, that's a fairly near-term roadmap item for the console team. But that Image Hub, that sample app, is an interesting one to play with, in part because I think it begins to help expand people's horizons. In part, I think Deepak had a question earlier about filtering ingress traffic and manipulating it, doing some things with it. The Image Hub, that sample app, is an interesting take on that. It actually enforces multi-tenancy and a bit of a subscription-based pricing. That intelligence is not built into the sample app itself, but that intelligence comes from the WASM filter that you can see in that sample app. So pretty cool to explore the power of the data plane in that way. Which I'm, so just, I don't know if there's no, I guess there is another question. And so the question is, in multi-OS clusters, do you have a recommendation for Windows nodes?
I don't know how to answer that, because I always use Linux.
There is a particular attendee with us, a Docker captain, Nuno, who's in attendance, much more of a WSL2 Windows expert. And so I no doubt he'll be in the same Slack channel with us as we conclude. So we'll point you to the experts there.
We are not able to hear you.
Oh, okay.
Yeah.
It's not a volume thing, huh?
Cool. No more questions. Yeah, so feel free to connect with us on the Slack, and any additional questions, we'll try to get the recording fixed before we make it available for you for the viewing, general viewing.
Cool. Very good. I don't know if you guys can hear me now or not, but I'm going to say something anyway,
Yeah.
which is,
We can.
okay, good. Well, since this talk couldn't have been any more of a disaster from the out of sync things and the microphone going dead, and I'll say that I want to say thanks, Prateek, actually, for all the work that you've done on this. It's very interesting analysis that you've done. Pleased that you were able to use Meshery as much as you did. I think you about wore the rubber off the tires on it. But I'm really excited about empowering people with the knowledge of how much each of these functions costs. And it's thanks to your work that they'll be able to know. You're going to know what it costs to rate limit.
Yep. So thanks, Lee, for the opportunity. Yeah, it was great.
Good. Very good. Well, I think we're out of here. We'll see you guys in Slack.
Yeah. See you guys.
Or y'all. We'll see y'all. Sorry.